Alright, ladies and gentlemen, we're going to work on our describing motion. This will be our motion part 2 for recorded notes for AP 1. And it's primarily about your free falling. Now, really, acceleration due to gravity. All bodies in free fall, that means that there's no air resistance, we're going to live in a perfect world, near the Earth's surface have the same downward acceleration of 9.8 meters per second squared. So it doesn't matter if it's the elephant or the rock, they're both going to have an acceleration of 9.8 meters per second squared. A body in free fall has the same downward acceleration whether it starts from rest or it has an initial velocity in some direction. Doesn't matter whether it has horizontal, vertical velocity, anything. Its acceleration rate, how much it's going to change between its velocities, is always going to be 9.8 meters per second squared when we're here on Earth. So let's drop a ball from the top of a cliff. What happens to the velocity each second? Well, if we start at 0, then after 1 second, it's going to be 9.8. After 2 seconds, it's going to be 9.8 plus 9.8 more, so that's 19.6, and then after 3 seconds, it'll be 29.4, so on and so forth. We can actually use our formula, the very first formula in the formula chart, and see if that truly works, changing the A to G for gravity, because really gravity is just acceleration, and then you could plug it in, 9.8 times 1, or 9.8 times 1, plus 9.8, because you have an original velocity, or you could just do 9.8 plus 2, or times 2, so both of those give you the same answer, or you could do 9.8 times 3. All of those would be ways to get the information. So what happens to the distance traveled each second? Well, using our formula of v naught t plus 1/2 at squared, which is our second formula on our formula chart, we could change that a also to a g, and then we do our 1/2 9.8 times 1 second squared. That's 4.9 meters. Then the next one, 19.6 meters, and so on and so forth. So it's really just a proportion, and it's using that acceleration rate of plugging gravity in for that, because gravity is acceleration. So let's look at a coin toss. If the coin starts at 6 meters per second, and I toss it up into the air, it is going to immediately decelerate. It is going to travel, or it's going to slow down as it goes up. The coin is going to begin to decrease the minute it leaves my hand. And that deceleration rate is going to be a negative 9.8 meters per second squared. Now the velocity is 0 at the very, very top. As it switches directions, it's going to stop and change directions, just like it did when it crossed from quadrant 1 to quadrant 4 in our graphs. It stopped and switched directions. Then the coin is going to start its downward trip. So it's going to start from 0 meters per second, and it's going to then accelerate as it moves downwards. That acceleration rate is going to be a positive 9.8 meters per second squared. So what's its velocity when it gets back to your hand? Well, if it's the same exact distance as when you tossed it, it's going to have the same amount of time to decelerate to 0 as it does to accelerate from 0. So it should be the same velocity as it reaches your hand again. Should be 6 meters per second. That's because that time is the same. And if it has the same amount of time to accelerate as it does to decelerate, then it should be able to reach the same speeds, because they're both starting from 0. Let's look at another example of an up-down problem. If we shoot at this cannon off at 40 meters per second, then it goes up to 30, then it goes up to 20, then it goes up to 10. At the very top, its velocity is going to be 0. And then as it switches directions at the same location, it has the same amount of distance and the same amount of time to change its speed. So if it's matching horizontally in its distance and amount of time it's traveled, then it's going to end up being those same velocities. So going up, its deceleration rate is 9.8 meters per second squared negative, and going down, it's a positive 9.8 meters per second squared. Same rate, just negative and positive for the fact that it's going one direction versus the other. So that's helping with that directional information. Hopefully that makes sense. We'll talk more about this tomorrow in class and do some examples in our packet. See you then.